What point I showed up. So there might be a gap in the video. So my area here is basically, well, if I take this hoop, imagine I take the hoop out, I put a snip in it, and I just stretch it out, I got just a really long rectangle. Where the thickness of the rectangle is r d theta. And the length of the rectangle, well, that's just the circumference, 2 pi times r sine theta. That's the radius of the circle. So over here, we now have big G mass sigma times 2 pi big R sine theta times r d theta over s squared cosine alpha. Is there a question?
He was trying to figure out sigma.
Oh.
Okay, I have a question. What is the 2 by r sine theta on the square?
All right, so I have this hoop here, and so I'm trying to find the area of this, and so this bit right here was trying to establish that the thickness of it is r d theta.
Okay.
If I imagine I have this hoop here and then I cut it and stretch it out, the length of it, I basically have a rectangle with a r d theta. That's just so badly drawn. R d theta is the thickness, and the length is just the circumference of the circle.
Okay.
So 2 pi times the radius of the circle, which is r sine theta.
No.
All right. Any other questions up to here? All right, so let's now collect the things that are constant. That no matter where I am on the circle, that it's always going to be the same. Big G mass sigma 2 and pi, those and r. Those are constants. I can just pull those up front. So G L sigma 2 pi big R squared times sine theta d theta over s squared cosine alpha I hat. Let's make sure I didn't leave anything behind. In Calc 2, what have you gotten to so far?
Right now, we're doing RNA.
Arc length and surface area.
Okay.
Revolve.
So you've done integrals at this point.
Oh, yeah.
Yeah.
Now we're doing something else, just repeating ourselves, chapter 7
Yeah.
seems to be.
Now notice I have this force which is dependent upon, well, I have 3 different variables here, theta, s, and alpha. We are going to move, I hat's also going to go out front. So what I'm going to do is do an integral, but I need to get them all in terms of a single variable. And so f is equal to, take our constants, g m sigma 2 pi r squared I hat. Integral sine theta d theta over s squared cosine alpha. And do a quick check just to make sure that, let's see, sigma 2 pi g, okay. Take the dx on that too. So now let's start getting them in terms of a single variable. If we look at the triangle here, and it's in green, I'm looking at the triangle that M to C to Q and back. Law of cosines. S squared is equal to little r squared plus big R squared minus 2 little r big R cosine of that angle right there, which is 180, I guess it doesn't matter if I'm using radians or degrees here.
Yeah, 180 minus theta.
Let's stick with radians. So pi minus theta. Cosine of pi minus theta is, let's see if that's, that should be, it's negative cosine theta?
Too small.
Yeah, that's negative cosine theta. This negative cosine theta. So moving now at s squared is equal to little r squared plus big R squared minus 2 little r big R plus 2 little r big R cosine theta.
How did that go to negative cosine theta?
Why is that negative cosine theta?
Yeah.
Wait, sorry, you were asking how to?
Yes.
Cosine of a minus b is cosine a cosine b minus sine a plus sine a sine b. So this is pi, pi and theta. Cosine of pi is -1. Sine of pi is 0. So that term drops out, and we'll have the negative cosine of theta. All right, let's take a derivative. Let's look at the differential here. So this becomes 2s ds equals 2r dr.
You wanna keep
So r is actually set there, so. Is equal to 2r big R negative sine theta d theta.
Because those are constants.
Yeah, for the problem. So big R is the radius of the circle, it's a constant, or radius of the sphere, it is a constant. Little r is constant because I'm looking at what is the force action on this mass that is a distance r from the center. Changing where the hoop is doesn't change the value of little r or big R. And so now, hey, here's the sine theta d theta. Let's solve for that then. So sine theta d theta is going to be equal to 2s ds over negative 2r big R, which then becomes negative s ds over little r big R. And I can make that substitution now. So I'm left with, instead of having to write this over and over again, I'm just going to make this equal to the letter p. So it's p times over here, sorry. This is equal to p I hat integral negative s over little r big R ds over s squared cosine alpha. That is equal to that. And s is going to cancel out. Little r and big R are constants for the problem, so I can just pull them out front. And so that would be equal to big P over little r big R negative integral ds over s cosine alpha. I've now gotten rid of a variable.
I had something there.
Yes, it would be. All right, so now, questions here before we solve for cosine alpha and get it in terms of S. All right, so
You can tell by the way that it is.
all right, so, hey, cosine alpha, we just did a law of cosines using this angle down here and that as our starting point. We have big R squared is equal to little s squared, or s squared, plus little r squared minus 2rs cosine of alpha. Just law of cosines using the same triangle, just doing r squared to start out with instead of s squared like we did last time. And therefore, big R squared minus s squared minus little r squared divided by negative 2rs is equal to cosine alpha. Or we can do little s squared plus little r squared minus big R squared over 2rs. And we pop that in for cosine alpha, and we're now down to a single variable. So the force, technically there's a vector here, is equal to negative p over little r big R I hat integral ds over s times s squared plus little r squared minus big R squared over 2rs. So we just made a little substitution right there. That. All right, so this 2r here, this 2 little r, we can actually bring that out front to make this a 2r squared out here. And we're left with ds times s squared plus r squared minus big R squared over little over s squared. I guess in math class, you usually put the differential at the end, but there's no problem putting it at the beginning. I guess when you get to calc 3, I suspect you put it earlier in, or maybe that's just my memory of it. Now we can't just do a straight integral from this, but we can break it up. So what I'm going to do is I'm just going to take a look at this part. I'm going to leave the constant, the coefficient up front. It's still there. I'm just not going to write it down. So this becomes the integral of, well, we're going to break this into the fraction of the s squared over s squared, so ds plus the integral of ds r squared minus big R squared over s squared. We can do one other thing. Because we have a single variable, we can now actually put in our limits of integration. S is the distance from M to the point on the sphere. So what is the largest value of S?
Wait, the largest value was.
Yeah, S is my variable here, so that's what I'm doing my limits based on. Nope.
No, not circumference, I mean diameter.
No.
Distance from Q.
S is the distance from point M to a point on the sphere. What is the largest value?
S. MQ. Big.
MQ.
MQ? That would be a sort of geometric way of expressing, I guess S is the length of MQ.
Yeah.
But in terms of things concerning the sphere itself,
Big R.
The largest value would be D minus.
what is D?
The diameter.
Okay.
But no, it's not. It's not.
All right, where, at what point on the sphere is S the largest? I got the sphere here.
Q.
Where on the sphere is S the biggest value?
At Q. Directly.
Well, where is Q then?
Just
R sine theta?
straight to the right of it.
Right there. So when Q is here, so what is the value of S when Q is here?
The radius,
S
big
is-
R plus little r.
Yeah, this distance right here, the big R plus little r. What's the smallest value of S?
Big R minus little r.
The first integral, simple enough, that gives you S from big R minus little r, big R plus little r. Plus, well, in essence, we have a S to the negative 2 here. So we, little r squared minus big R squared, integral ds, big R minus little r, big R plus little r, S to the negative 2. Yep, parentheses there. Way up here. So we have S from big R. Now we'll do that substitution in a moment. Big R plus R. What is the integral of S to the negative 2? ds.
So the S to the negative one over
S to the
negative
negative
one, so
one.
it's negative S to
I think you two just said the same thing.
whatever S to the negative one.
So negative S to the negative 1.
Yeah.
From,
R plus R, well, from R minus R to R plus R.
so now let's plug in the top one. So we got big R plus little r minus big R minus little r plus R squared minus little r squared minus big R squared times 1. I'm gonna bring that negative out front. And then 1 over big R plus little r minus 1 over big R minus little r. We're approaching that moment of truth. Find out if we made a camera center somewhere. This right here, big R cancels out, and what I'm left with is 2 little r minus. If I distribute this, because this is R minus big R over R plus big R. So it's going to cancel out the first one, so I'm left with little r minus big R. Minus. This will cancel out with that, leaving behind a negative 1. So plus R plus big R.
Is there any way we can close the door or?
I think there is a way.
Is there? They do have hinges.
Success.
Appreciate it. Why?
Yeah. And so now, we're left with 2R minus, well here, the big R's cancel out, and we're left with 2R equals 0.
I am not happy.
What's the zero?
Why?
For some reason, students find it very frustrating to go through all that and end up with 0 in the end.
Yeah, yes.
I look at that and I'm going, we went through all that and came up with a really simple answer.
I mean, yes, but. I'd rather go value.
Alright, so what this says is that if I have a sphere of mass and a hollow sphere of mass, and I have at some point inside of it, there's no gravitational force acting on that mass. There's no gravitational pull because it's equally pulled in every direction. From a conceptual point of view, I have a sphere here. It is definitely, it's being pulled in every direction. Now, the part that's closer to it, it has a much stronger pull to it, but there's less close to it than there is far away, and it balances out. I have less mass, the mass is farther away over here, so it's a weaker gravitational pull. However, I have more of it. I have more of the weaker pull than the stronger pull, and it balances out. There's a very similar derivation done in 252, except dealing with charges, and that has a much greater impact than what we're doing here. Questions here before I'm going to hand wave through the second half of the derivation. Any questions here before I talk about what happens if little r is bigger than big R?
That's saying if it's outside.
Yes. Just with more words. All right, so if the mass is outside of the sphere, you can go through the entire derivation again and don't end up with 0, but what you end up with is if the mass is outside, the force on that little mass becomes, or the magnitude of the force, becomes big G times, the mass of the sphere, times the mass of the tiny little mass over r squared.
Huh, that seems familiar.
In other words, if you are outside this mass, this spherically symmetric mass, you can treat the mass like a point charge at its center. Or sorry, not point charge, point mass at its center. Some semesters I do the 0, some semesters I do that one. And the only difference is limits of integration change. Everything else is the same until you get to here. So we can now figure out what is the gravitational, if I plotted gravitational force versus distance from a solid sphere, we can now do that. So now back to what I started with, a solid sphere. I'm going to set up my coordinate system here. So this will be force and R. This is the point where little r, where the radius is equal to the radius of the sphere, or the distance between the two masses is equal to the radius of the sphere. So outside of it, I could treat this like a point mass, and so it's just a 1 over r squared relationship, where that point right there is equal to big G, mass of the sphere, mass of the one outside of it, over the radius of the sphere squared. That's that value right there. Oh, I should dot that because that's not actually part of the graph, that's just pointing to that, what that value is. Once I'm inside the sphere, once I'm inside the sphere, I can start neglecting some of the mass, any of the mass that's outside of that point. So if I have my solid sphere here, and with a center there, and I have a point here, any of the mass that's outside of this small little radius here is not contributing to the gravitational pull on the mass, on my little m here. And so now I can treat anything within that radius as a point mass at the center. So if I assume that this sphere right here is a density rho, a uniform density, which is mass over volume, or dm over dv, however you want to write it out. So gravitational pull on a mass at this point right here would be big G times the mass of this small little sphere here. Well, the mass of that small little sphere would be rho times the volume. So it would be rho times, well, the volume of that sphere, which is 4/3 pi little r cubed times little m over r squared. Since the density is uniform, no matter if I take a look at a small part or a big part, the ratio is the same. And so the density is the mass of the entire sphere over the volume of the entire sphere, which is 4/3 pi big R cubed. If I plug that in, this becomes big G, big M over 4/3 pi big R cubed times 4/3 pi little r cubed little m over little r squared. We got some canceling out that we can do. The r squared cancels out with 2 of those r squareds. 4/3 pi cancels out with 4/3 pi. And I'm left with big G, big M, little m over r, big R cubed times little r. In other words, once I'm inside this uniform sphere, the gravitational pull is now linear. It goes from a 1 over r squared relationship to a linear relationship, ending with the expected value of the gravitational pull in the center is 0, because you're pulled equally in every direction. That is a sad read. And so we have a plot of force versus distance from center from this uniform density sphere. Questions? So in terms of what we've covered, we've done the gravitational force, obviously, we did the Kepler's laws, we've done the centripetal motion problems for car going around a ramp. We've not done car going.
Like an incline, like facing inward?
Yeah. Okay. Then let's do it. Actually, let's take a 5-minute break. Stretch your legs, wake up, whatever you need to do.
Actually, you help me. Just help my hand. He was looking kind of killer right here. Yeah, no.
You want your
lemon tea, bro.
Excuse me. Rest in peace, Arnie Palmer.
What's making you say that? He was here last class. He missed the test.
I saw him today.
Oh, you saw him?
How much you boy? Yeah, I saw him today.
Steven.
I got too many numbers.
I hear you. It's, I feel like we fall into that.
Right?
Everybody else does it, so we start doing it too.
I still know
It does.
I see you 3 times a week.
It's one of those critical, imagine like you walk into like some water, like you flew into some country and the culture was like, listen, if you touch me, like,
Water.
you water. It's like one of those, you learn it fast, right? It's like,
So you have it.
I'm touching it anyway.
It seems like that's backwards now, but it's still not exactly something that hard.
It's delicious.
Even if it's negative. So you use the experimental acceleration.
Oh,
Yeah, he's pretty good.
Yeah, if you take.
Even though today we did a circle.
to the gym.
Yeah, I'm not even sure what you're
Alright, so your theoretical
Oh,
force.
yeah, I hadn't recovered one. I just did.
It's,
Yeah, the issue is the
Some are
fact
gonna be
that
in.
that's backwards.
Okay.
And so if you brought F over
I
on
just
the
like
other
how
side,
we
you
did
end up
on
with big F minus. in
You're
there.
calculus too?
Difference there.
I feel bad, you got calculus
Which
three,
would significantly drop
and then you got.
that value.
I ain't taking,
Equations,
I ain't
which is
taking.
terrible.
I ain't
Thought it
taking
was
calculus.
I
significant.
just think Bulger wasn't that good for that class.
I gotta see.
It was horrible.
Yeah, that's best to go. Or you could just skip a negative, you're saying up the range is positive.
Basically have to retake it or.
I think I meant to say.
I would've went in there, I would've.
Well, I mean, what I'm saying, if you're going up the ramp,
Yeah,
it's
you
positive,
transfer
then your acceleration is And so instead of
Well, somehow.
messing with all that, you could
I
just
think
make
if you even-
some ramp positive and just make it negative.
Yeah, you can get a degree with D though, like, that's what I understand.
I tried everything with the correct.
I wasn't dumb.
14 years. I should get some.
But I like how I had the take home test though. I'm all
Yeah.
for
For
that.
all of them?
Because,
I didn't ever take, not in California.
well, it's cause I think
It
it's.
depends on how you wanna look at it. You should get a lot of values close to zero.
I should do that.
Now, some of them might be a little bit.
Wait, see,
I went in there personally on the last day, cause I had a
It should be,
62.
it should be close to each other.
Yeah, see?
Just depending on.
Yeah, it's
The
terrible.
question is point
Yeah, one, I said, here's the deal. I was this close to him, cause I got.
Yeah, in the scheme of things, yes, they are close to each other.
I don't want
The
to, it's not even.
difference between the two, well,
I want you to look at me
the
and
percent difference
tell
would
me,
be.
I get a C or no, I'll give you a D or better.
Divided by.
So I went in there and turned over the test and said,
0.7.
alright, so I tried really hard.
So,
Can I get a C?
like, you really need, because you're dealing with such tiny
Here's
numbers
mine.
there, you need
I know,
more fluctuations too.
I also would have got a D, but she gave everyone
I
like,
would
you
consider
get a
those
C
close.
for transfer purposes, so I got a C.
But I mean, it is.
Maybe since I got a D, you could also do the same thing, transfer. Transfer purposes.
Right, it should be
And
just one number.
I'll see what I can do, I'll see if I can
Depends on how
promise it. We
sophisticated
get
person
C,
is.
I'm thinking maybe, I'll see what it comes out to.